Alrighty, so some questions about finding all possible solutions to a polynomial, especially when it's not factorable. So we're going to find both the real numbers and the complex solutions if there are any, meaning containing imaginary parts. So the first thing that we have to do is list out the possible rational zeros. Now I've gone ahead and done that. So remember, the way that we determine this is we look at the factors of p, and p is always going to be the constant term in the polynomial. It's going to come last if it's in standard form. And then we want the factors of q, which is the leading coefficient of your polynomial. So the factors of 8 are positive 1 and negative 1, positive 2 and negative 2, positive 4 and negative 4, positive 8 and negative 8. And the factors of q are just positive 1 and negative 1. So that means we have 8 different possibilities of possible rational zeros. Now, we need to test to see which ones are. Now, we could start guessing and checking, but as we talked about in class, we can use technology to help us out a little bit here, which, let's see, I'm getting an error message here. I'm going to pause this for a second. Okay, so let's look at the graph, and here's what it looks like. Now, on your graphing calculators, it's not quite as obvious where it's crossing. It might look like it crosses exactly at 1, but we can't be sure until we actually test those values. But it does look, by looking at this graph, like it probably crosses at negative 1, positive 1, and positive 2. So we want to keep those in mind because those are going to be the values that we want to test. And we'll test them by using synthetic division, since they're all linear factors. If they are zeros, then they're going to divide out evenly. So I'm going to start by testing positive 1. So we set this up with all of our coefficients. So we have 1, negative 2, 3, negative 6, negative 4, and positive 8. Okay, so look at your notes on synthetic division there if you need to. We always bring down the first number, and then we multiply 1, and we add negative 1. Multiply, negative 1, add positive 2. Multiply 2, add negative 4. Multiply negative 4, add negative 8. Multiply negative 8, add, we get 0. And that's exactly what we wanted because a remainder of 0, which is our last number there, shows us that that divides in evenly. So what did we just figure out? That this factors to x minus 1 times x to the 4th minus x to the 3rd plus 2x squared minus 4x minus 8. We went down by 1 degree. We started with a 5th, then we divided out 1 power. So now we're at x to the 4th. Okay, problem is what I have left is also not factorable. It's too big. So now we need to go back to that list that we kept in our head. We had negative 1, positive 1, and positive 2, and we need to try another one. So I'm going to try positive 2. So I'm going to use the new one that we got there. So this is 1, negative 1, positive 2, negative 4, negative 8. And we'll just run through that algorithm again real quick. And ta-da, you can see we come out with a remainder of 0 yet again. And so now what do we know? Well, we have the x minus 1 that we already knew. Now the x minus 2 that we just got. And now we have what's left, which is x cubed plus x squared plus 4x plus 4 equals 0. Now, we could look at this one more time and see that we have this left, and we need negative 1 to factor out, because that was the other one that we saw in the graph. Or I look at this one and I notice that if I split this down the middle, factoring by grouping is going to work. I can factor out an x squared, and that gives me x plus 1. And I can factor out a 4, and that gives me x plus 1. Whoops, I didn't mean to write that. And so now I know that this factors to x squared plus 4, x plus 1. And so I'm going to bring all of these factors up here now, and let's see what we've got. Our new equation now is x minus 1, that was the first factor we factored out, x minus 2, whoops, that was the second, and now the third factor became x squared plus 4 times x plus 1. And all of that is equal to 0, okay? So to get our solutions, we're going to take every single one of these equations and set them equal to 0. Now, we usually do this in our heads. So x minus 1 equals 0, but I'm going to write it out so that we can see. X minus 2 equals 0, x squared plus 4 equals 0, and x plus 1 equals 0. That's that 0 product property. If they multiply to make 0, at least one of them has to be equal to 0. So we get x equals 1. That's a rational solution. X equals 2. That's a rational solution. Whoops. And the last one, we get x equals negative 1. That's a rational solution. Now, we expected all of those because we saw them on our graph. This middle one is where the complex solutions come from. So I have a quadratic. So we have lots of different ways to solve a quadratic. We might be able to factor it. This one is not. We might be able to complete the square. We don't have an x term, so we can't do that here. Quadratic formula is always great, but that's always going to be my last resort. Or we can use solving by square roots. And because I'm able to get the x squared by itself pretty easily, that's the method I'm going to use here. So I'll start by subtracting 4 from both sides. And then I have to take the square root of both sides. So I get x equals plus or minus because we put the square root in there. Now, the square root of 4 is 2, but the square root of negative 4 is going to be 2i. And so that's where the complex solutions come from on this problem. And it could come from all kinds of ways. Maybe you do the quadratic formula and you get imaginary numbers. If it's factorable, you're not going to get an imaginary number. But if you do square roots or the quadratic formula, you might end up with imaginary numbers. So it just depends on what you have left. And that's why we end up with complex solutions on this problem.